Alright, this is the Chapter 13D Constant Velocity Problems flipped lesson. So we're going to be going through a couple of different things here related to lines made with vectors. First of all, just looking at how we translate a problem into a vector equation. Then we'll look at some applications. And finally, we'll look at how the velocity and speed are related to each other. So let's start out first of all with how we translate a problem into a vector equation. So we have this problem, find the vector equation of a boat initially at 2, 3, which travels with a velocity vector of 4, -5. Then it says the grid units are kilometers and the time is in hours, and we'll use that for our next portion here. The first thing to do though is to remember that our basic vector equation for any line given a starting point and a velocity is this vector v equals a plus bt. And notice v is a vector, a is a vector, that's a position vector for our starting point, which in this case would be 2, 3. And then vector b is your velocity vector, it's also known as the direction vector. And in this case that's 4, -5. Alright, then of course t is our time. So when we translate that and plug in what we were given for this equation, we have the equation here, v equals the 2, 3 plus t times 4, -5. All right, and recall that you can then sketch this. All right, if we have our coordinate plane here, simply start with your first point. In fact, I'm going to get an actual grid here. It'll be easier to work with. Okay. All right, let's get rid of the lines here that I've got. All right, so we plot our point 2, 3. And here's 2, 3. All right, the position vector is also 2, 3. Okay, so there's our position vector here, 2, 3. Then we're using the velocity 4, -5. So we're going to go to the right 4 and down 5. This would be our point when the time is 2. Right, so if we wanted to look at this line, it's going to go through these 2 points. Now you'll notice I have it continuing on to the up and to the left, and those would be when our time was negative. Here's time 0, here's time 1, and we could keep going, here's time 2, and so forth. Alright, so that's how we could graph one of these vector equations. Okay. So now, how do we use this? Alright, let's take a look at 2 parts here. We have our equation. I have the reminder here, our units are in kilometers and our time is in hours. So we have 2 things here. First of all, locate the boat's position after 90 minutes. Alright, now notice 90 is given in terms of minutes. Our time is in hours. So we need to convert that to 1.5 hours. Then it's simply a matter of plugging it in for t and finding the resultant vector. Alright, so we have 2, 3 plus 1.5 times 4, -5. And this is similar to our rate times time equals distance. Here's our rate, or our velocity, times the time, and we're going to add those horizontal change and the vertical change to our starting point in order to get where we end up. Right? So we multiply by the 1.5, we get 6, -7.5. You add these 2 vectors together, and you get the vector 8, -4.5 as the result. So that's the point, that's our location after 90 minutes. Okay. The second part here how long will it take for the boat to reach the point 5, negative 0.75? And I would add to this question kind of another question, that is, do we actually reach the point 5, negative 0.75? And the way we can tell that is we need to be at 5 horizontally at the same time we're at negative 0.75 vertically. So how do we do that? Well, here we're going to look at our parametric equations for x and y. X is going to be 2 plus 4t. And in this case, we want that to equal 5. So when we solve that equation, we get 0.75 hours. So we're going to be at the horizontal position 5 after 45 minutes, or 0.75 hours. All right, so preliminarily that's what we would say our answer is, but just to double check, let's look at our y parametric equation. That's going to be 3 and then minus 5 times t, so 3 minus 5t equals a negative 0.75, because that's the vertical position we want to be at. All right, so when we solve this, we subtract 3 from both sides. We get negative 5t equals a negative 3.75. And then when we divide by 5, we indeed do get 0.75 hours. All right, so the fact that these times are the same confirms that we do actually hit that point, and now of course we know when we hit that point. One side note here that I would like to point out, just to reiterate something we've mentioned in the past, is the idea of speed. You know, how fast is this boat actually going? When we're talking about speed, we're talking about our velocity vector, and specifically the magnitude of that vector. All right, so if we think about our magnitude formula, we have the square root of 4 squared plus 5 squared, or negative 5 squared is the same thing. So that's 16 plus 25 is 41. All right, so we're taking the square root of 41, which is approximately 6.5 kilometers per hour. So we're cruising along, not going too fast here. Okay, since we're talking about speed though, let's consider a situation where we know the direction, but we want it to be a certain speed. In other words, we want the magnitude to be a certain value. Here's the situation. We want to convert a direction vector to have the speed we want. So we have this eagle swooping down, and it's going in the direction negative 2i plus 5j minus 14k. But that's just the direction. If you find the magnitude of that, that actually does not equal the speed we want, 90. Okay? So how would we go about doing this? Well, if you recall earlier in this unit, we talked about how to get a vector to have a certain magnitude. Well, magnitude is speed. So what we're going to do, if you recall what we did, is we used a unit vector. That's a vector where the magnitude equals 1. And then you simply multiply that unit vector by whatever the magnitude you want is. All right, so in this case, we're going to take 90 times the unit vector. All right, so the first part of getting our unit vector was to find the magnitude of the direction that we want to go. So again, we're using our magnitude formula. So it's a square root of 2 squared plus 5 squared plus 14 squared. And that all adds up to 225. And the square root of that is 15. So to find the unit vector, what we would do is we would multiply this vector by 1 over 15. Okay? And I'm actually not going to simplify that here, because rather than dealing with 2 fifteenths and 5 fifteenths and negative 14 fifteenths, I'm going to just go ahead and do this last step, because I need to multiply to get a speed of 90, I need to multiply that unit vector, here it is, by 90, okay? And if I do the 90 times 1/15 first, I just get 6. And then when I multiply my direction vector by 6, I get -12, 30, and -84. So that is the velocity vector that has a speed of 90 kilometers an hour. Okay, and you'll see problems like this presented various ways. One might say we want our velocity to be parallel to this given vector. It's the same situation. Okay, so in class we'll be looking, working through some problems here on page 330, 3, 5, 8, and 9. For all of these that are in 2 dimensions particularly, draw a picture. In fact, all of these ones are in 2 directions at this point. Draw yourself a picture. That'll really help, especially on parts like 3C. When is this car due north or due west of our origin? All right, being able to see that is really helpful. Okay, and that's it for the lesson, and have a good day.